The input is the set of x, the output is the set of y. When you do the vertical line test, you always better know the reason why. With tables and graphs, diagrams, or equations like f of x. The set of inputs is the domain, the set of outputs is the range. When no x repeats, you'll have a function. The set of inputs is the domain, the set of outputs is the range. When no x repeats, you'll have a function. A function is a type of relation, but a relation is not always a function. An input may have more than one output, an output may have more than one input. When every x has exactly one y, we give that a special name. A function! Yeah! The set of inputs is the domain, the set of outputs is the range. When no x repeats, you'll have a function.
Well, welcome back, algebra students. As we're again learning about functions. Our last lesson we were learning about the functions, domain and range, and so that song was kind of a bit of a review of what we did last lesson. We're going to also look at some more functions in this lesson in 3.2. We're looking at linear functions from the Big Ideas curriculum. And so what we're going to do here, as you can see, what we're going to learn is identify linear functions using graphs, tables, and equations. In the song at the beginning referenced that. We're also going to graph linear functions using what's called discrete and continuous data. We'll find out what that is, and then a real-life problem there at the end. First, let's go ahead and look at our cartoon for the day. So here's a bird's nest there with a big soccer ball inside. It says, Gabrielle, Grace, what did I tell you kids about playing soccer in the nest? There's no room for anything else. Alright, and maybe your mom says no playing ball in the house, no playing ball in the nest. Alright, let's get into our linear functions now. Okay, so with linear functions, we're going to start with just identifying linear functions. To be able to identify them, they definitely have certain characteristics that we should be able to just look at them and see that this is a linear function. So you have some vocabulary here highlighted for you. So you want to make sure you write this down in your vocabulary section. And so a linear equation in two variables, x and y, is an equation that can be written in the form of y equals mx plus b. So that's definitely the form of the equation of a linear equation, where m and b are constant numbers. So the m is a number, b is a number, but the y and the x will stay the letters, stay the variables. The graph of a linear equation is a line. So that's another characteristic of a linear function. In fact, the word linear starts off with the word line. And so we can see that's what the graph's going to look like. It's going to be a line. Likewise, a linear function. Okay, so there's a linear equation and then a linear function. Now, a function is typically given in like a function notation, like f of x. So a linear function is a function whose graph is a non-vertical line. Now, a vertical line would not be a function. A straight up and down line would not be a function because it would not pass the vertical line test like we saw in the last lesson. A straight horizontal line goes straight across is okay. It says a linear function that has a constant rate of change can be represented by a linear equation in two variables. So there's another thing about a linear function that has a constant rate of change. A nonlinear function does not have a constant rate of change. And so that means that the graph is not a line. So just to sum up this little section right here, here's some things that you want to understand about linear functions. A linear function is a graph of a line. The graph is a line. And then secondly, it has a constant rate of change. We're going to see that there in a minute, that it will constantly be changing at a constant rate. And then another thing is that you can have an equation of y equals mx plus b. That will also be a characteristic. If the equation is in that form, it's a linear function. Also, it also might have an equation this way as well, which is the standard form of a linear function, just ax plus by equals c. It's another way the equation might be that you might see often enough. And so you need to realize that the x in both of these equations is just an x. There's nothing going on with the x. There's no absolute value signs around the x. There's nothing else happening with the x. All right, so let's move on. Actually, down here is a couple of things I wanted to show you, and you're not going to need to write these down. We're just going to go through these together, just identify with these graphs which one represents a linear function. Obviously, on a graph, you can see the graph is a line. So definitely B is our linear function. A is not a line, so A is not a function. So graph is not a line there. So it's not function, it's nonlinear. We call it nonlinear. The graph is a line, so it is linear. Here's a couple more that we can look at. So we can see the tables here. There's a couple of tables. Now the tables are always ordered pairs. You have x coordinates, y coordinates, so 336 is an ordered pair, and so on. So whenever you're looking at a set of ordered pairs, especially in a table, you want to look for that constant rate of change. So between 3 to 6, that's changing by 3. Changing by 3 again to get to 9. Adding 3 again. So you're constantly adding 3 on there. So it means you have to constantly do the same thing this way. 36 to 30, you're subtracting 6. You're subtracting 6 again, subtracting 6 again. So you're constantly doing the same thing. As you can see there, adding 3 there, subtracting 6 there. That's a constant rate of change, so that is a linear function. But if you look at this one, number or B, 1 to 3 is 2. Again, another 2 and another 2. That's constantly changing. When you go down here, 2 to 9 is 7. 9 to 20 is not 7. So you can see there's a constant on the x, but there's no constant change on the y. So because there's no constant rate on both x and y, it is not a linear function. Okay, so now having seen those examples, I'm going to have you try 1 through 4 on your own. So I'm going to have you pause the video. So 1 and 2, just identify if it's a linear or nonlinear based on the graph. 3 and 4, identify if it's linear or nonlinear based on the table. Okay, so I'll give you some time. Just pause the video and then play it to check your answers. Okay, so you should have paused it. You should have some answers. All right, so your answer here for 1 and 2, you can see definitely number 1 is not a line, so that one is not linear. And number 2 is a line, so that one is a linear function. So very clear right there. Again, the only line that is not a linear function would be a line that would be perfectly vertical, just going straight up and straight down. That would not be a function at all. Number 3, you're looking at the rate of change on this one. So you're looking at the rate of change up on top. That's going adding 1 every time, so it's constant on the x. And then for the y, it's adding 3 every time, so it's constant on the y. So yes, that is linear as well. Number 4, you're again looking for rate of change on the x. It is constantly going up by 1 every time, so you're good there. But when you look at the y's, you're not constantly going up by the same amount. It's going up by you actually went down and then you went back up, and then when you went, so it's not a constant rate of change on 4, so that's not a linear function. Okay, so again, here's a couple more examples before we look at the next couple on our extra practice. We're looking at equations now. Still the same thing. Which of the following equations represent linear functions? So there's a few different ones here. They're separated with a comma. So you have your first one here, then the next one. Let's see, there's 1, 2, 3, 4, 5. Looks like 6 different types of equations. You don't need to write these down. You can if you want to. They are in the book. But you can just watch this so we can get the idea of what is going, when we see an equation, how can we identify that it's linear? So your first one, y equals 3.8. So y equals 3.8 right there. Basically, if you can write any of these equations in a y equals mx plus b format, then you know that it's a linear function. So we could do that. Even y equals 3.8, that's going to be in y equals mx plus b. It's just the m would be 0. So yes, that's a function right there. This one here, y equals a square root of x. Well, that's not a linear function. The square root of x is not going to be able to be just an x. So definitely not that's a square root function. This one here, y equals 3 to the x power. Well, x is in the wrong spot there to be linear. It needs to be down here, either just right here as an mx, a number in front of x, but it has to be basically just an x there, plain x. So the location of where x is very important. It can't be underneath any other symbol. It can't be inside of any other symbol. It can't be as an exponent. It can't be even as a denominator right here where it says y equals 2 over x. It can't be in the denominator. So that's again not a linear function. Y equals 6x minus 1. This one you can. If we distributed the 6, it would be in this form, mx plus b. So yes on here. And again, on this one, x is being squared. X can't be squared. You can't be doing anything to the x like that except having a number right in front of it, a coefficient number that's just multiplying x. So basically your x can be multiplied by something, or your x could be added or subtracted by something, but it can't be doing any of these other fancy things like being squared, being a denominator, being in an exponent position, being underneath or inside of any other symbols. So that's what we're seeing here. So you can say you can rewrite these. So these ones here, those ones are the ones that represent the linear functions, just those two. All right, so again on 5 and 6, you're just determining whether the equation represents a linear or nonlinear function based on the equation. So what we just talked about, go ahead and pause the video and get an answer for 5 and 6, and then play it to check your answer. Alright, so hopefully you got a couple answers here. For number 5, this equation y equals 3 minus 2x. Again, y equals is fine. Alright, the x is really where you want to focus on. What's happening with x? Well, you're just multiplying it by a negative 2. It's also being kind of added by a 3. That's fine. In fact, you can move this around. Just switch the order, put negative 2x in front, then plus 3. That's a linear function right there. So your x, your y is good, your x is good, it's linear. Okay, nothing fancy happening with x. Number 6 though, if we look at where the x is here, y is fine, y equals, but something's going on with x here. It's getting kind of fancy when it's being cubed right there. So that's not going to be a linear function, that's actually a cubic function. We'll call that a cubic one. So that's non-linear, it's not linear. Alright, let's keep moving forward. Alright, so we will pause right now just for a little quick joke of the day. What do you call a dinosaur with an extensive vocabulary? What do you call a dinosaur with an extensive vocabulary? Well, a thesaurus, of course. Well, a thesaurus. Now, hopefully you know what a thesaurus is. I mean, with the way computers are now, we don't need a thesaurus as much anymore, but I know when I was in school, we had a dictionary and then we had a thesaurus. So if you don't know what a thesaurus is, ask your parents and they will let you know. Alright, so real quick, I just wanted to mention this concept summary that's there in your notes. It's the representations of functions. So there's different representations for functions. In fact, this would work for any functions. You can see a function just by words. You know, an output is 3 more than the input. You know, so you can use words to describe a function. You can describe a function by an equation. You know, y equals some equation. This would obviously be linear functions here we're talking about. They're all the same function here. So this would be the words for this function, the equation for this function. You could do an input-output table, okay, a table of values we can call it, where you have x on one side, y on the other. These are all still ordered pairs here. -1, 2, 0, 3. It's a constant rate of change, as you can see here, for a linear function. You could also do it by a mapping diagram, where it's kind of this like little map with got bubbles around your inputs and your outputs, and then one input here is mapped to the output. So the arrows are mapping inputs to outputs here. This is a linear function here because it's definitely a function because every input is going to exactly one output. Okay, and again, the inputs are constant rate of change, your outputs are constant rate of change. You can also describe and represent functions with a graph. So we're looking at linear functions right now. We're going to focus on linear functions for quite some time. And so we're going to getting very used to these lines and graphing the lines there. So you can see all these points on this table are the points that are on this graph. It's the same ones that are in this mapping diagram. So you can represent functions in different ways. And you know, we're going to be seeing functions most often probably with equations and the table and the graph. Not so much here with this mapping diagram, but you can see it that way. Alright, a couple more things here. We have a vocabulary, a couple more vocabularies. This one you need to write this down here. where it says the solution of a linear equation in two variables. So what you want to write down for that is that it's an ordered pair, x and y is your ordered pair, that makes the equation true. So basically an ordered pair would be an x and a y, so if you think of that y equals mx plus b kind of form equation that we said a linear function has, you could plug in the x number and the y number, and if it makes a true statement, then that would be a solution of the linear equation in the two variables. The core concept here, discrete and continuous domains. So we need to understand what these words mean, and since they are in your core concept, you don't need to write them down, but you need to highlight them. Just go ahead and highlight them on your core concept. They are important. Discrete means that it's a set of input values that consist of only certain numbers in an interval, so it's only going to be separate points. So a discrete domain or a graph that is discrete is going to be just points on the graph, separate points. When it's continuous, then it's going to be a line of some kind or some curve or something where it's continuing from one point to another point. So this would be that a continuous domain is a set of input values that consists of all numbers in an interval. So from here to here, example, all numbers from 1 to 5. This would be just integers from 1 to 5. Well, integers would just be 1, 2, 3, 4, and 5 because integers are not going to be in between 1 and 2. That's not an integer. Integers are just the numbers. These numbers right here on a number line, those are the integers. When you ever hear that word integer, that's what we're talking about, numbers on a number line. We're not talking about fractions or decimals or anything like that. Negative or positive numbers or 0 on the number line. So a way we could write this out right here is we could describe this just like we did in our inequalities. We would use a compound inequality to describe the domain, this continuous domain. This one would be described by 1, 2, 3, 4, 5. That's listing the domain. But this one would be described as this inequality. 1 is less than or equal to x, less than or equal to 5. That would be our domain for this one and how to describe it. Alright, so here's just a couple here, A and B, just to watch these before we do our next couple problems on the extra practice. I'm just going to have you see if this is a discrete or a continuous function, and then what that domain would be. So letter A, as you could see, it's separate points. So when it's separate points like that, it's a discrete domain. And the domain actually would just be the x values of these starting at 0, all the numbers from 0 to 6, so that would be our domain. All the separate integers from 0 to 6, 0, 1, 2, 3, 4, 5, 6 listed in a row. Letter B, we can see now this one is kind of the same idea, but now we actually are connecting the first point with this last point, so it's continuous. This is a continuous domain. And so the way we represent this, since it's continuous, and we couldn't really be able to do this for a continuous domain, you would have to say, well, it starts at 0 and it ends at 6. X is between 0 and 6 for the domain. So from 0 is less than or equal to x, less than or equal to 6. Now we could talk about a range as well. You know, we talked about ranges before. That's the y values here. We could say the same exact range, 0 to 6. We would just change the x to a y when we're talking about range. But on this lesson, it's just asking us about domain. Okay, so for number 7 and 8, that's what we're going to be doing here. It says find the domain of the function represented by the graph. Determine whether the domain is discrete or continuous. So again, I want you to try these two on your own. Go ahead and pause the video and then check your answers once you've finished by playing it, and I'll let you know what these answers are. Alright, so your answer for number 7, this one you can see it is continuous because it continues. It's connected from your first point to the second point. So since it's connected there, it is continuous from 1 to 5. So from 1 to 5, that's where we were at. And so you can see that's what our thing is going to be. It is continuous. It continues from 1 to 5 here. That's how we would write our domain. That would be starting at 1 is less than or equal to x, less than or equal to 5. You're always going to use the less than symbols because you're starting with the smaller number and the bigger numbers on the right. Number 8, this one you can see, since there's separate points right there, it is discrete. And so you can see the domain for this is just going to be those numbers on the x-axis, just these 3 numbers here, 1, 2, then 3. That's our domain. It's just 1, 2, and 3, just listed with those 3 numbers. So it's a discrete domain, is always just going to be listed with this, just the numbers. Continuous is going to need some kind of inequality to describe the domain. Okay, so we're not quite done. I know you're done with the extra practice on 68, but I'm going to actually add 2 more problems to that page there at the bottom. And so what we're going to do is we're going to look at these here just as examples, and then we'll do a couple more problems on that page 68, and then also give you kind of a little end of the lesson quiz in just a second. So let's look at this one. So on the notes page on page 67, if you can go back to page 67, we can take notes on this. So you can be putting this on the notes page on page 67, in fact. So we could say this here, it says the linear function y equals 15.95x. So that is a linear function as your m. There is no b on this one, if that's we're going to be in that y equals mx plus b format. So it represents y, or x represents, no, the function represents the cost y in dollars of x tickets for a museum. Each customer can buy a maximum of 4 tickets. Okay, so you're limited to 4 tickets. It says A, find the domain of the function. Is the domain discrete or continuous? Okay, so we could think about, can we buy partial tickets? Can we buy half of a ticket or a part of a ticket? And we can't. You have to buy one whole ticket. So because we can only buy whole tickets, that means our domain is just going to only be whole numbers. So that's a discrete domain there. So our domain is going to be discrete. It's going to be just 0, 1, 2, 3, and 4, because this is what you could buy. You could buy 0 tickets, or you can buy 1, 2, 3, or 4 tickets. You can't buy any more than that because it says maximum number of tickets is 4 tickets. Letter B says graph the function using its domain. So if we just want to graph these points, okay, we can graph this on a kind of a coordinate plane. So we can make an input-output table just with these numbers. These are our input numbers for x, because remember domain is the x numbers. So we could do this. We're going to input our 0 through 4 into this function here, multiply by 15.95. So when you buy 0 tickets, you're going to have to pay $0. So output would be how much money you'd be paying. 1 ticket, 1 times 15.95 is just paying 15.95. If you buy 2 tickets, you multiply it by 2, now you're paying $31.90. If you buy 3 tickets, you multiply the $15.95 by 3, that gets you $47.85. And if you buy 4 tickets, that's the maximum amount of tickets you can get, and you would be paying $63.80. So now these are your ordered pairs then. The x with the y numbers creates the ordered pairs, and so we can put these on a graph. Since everything is positive, as you can tell, we're not going to be able to buy negative amount of tickets or pay negative amount of dollars. So that means that we could just only need to use the first quadrant of a coordinate plane. And that's what you see here. We call this an L graph. So the number of tickets are the x's, and that's what it says. X represents the number of tickets, y represents the cost in dollars. And so you have 0 through 6 here on our x-axis, and then 0 up to 70, 80 for the y-axis. And you just plot these points. 0, 0. You buy 0 tickets, you pay 0. You buy 1, you pay $15.95. You go over here, you buy 2, you pay $31.90. It shows just a little bit above there. And so you're just going to plot the points just like that. All right, so you can go ahead and pause this part of the video and finish up copying this down there on the notes section in page 67, because you want to make sure you understand how to do these charts correctly. We title them museum tickets. We got to label the x-axis. We got to label the y-axis with what they represent, and we then put our points on there. Okay, now in another notes section on page 67, because you have 2 places where there's a notes section, you can put this problem on the other notes section, whichever one you didn't use. And we're talking about cereal bars here. Cereal bars contain 130 calories. The number C of calories consumed is a function of the number b of bars eaten. Okay, so you're going to eat b amount of bars, so whatever number of bars you're going to eat, and then c is going to be the number of calories that you actually consume. So letter A says, does this situation represent a linear function? Okay, would this function be linear? We're told that it's a function, but would it be a linear one where it would kind of create a line? So that's letter A. So first of all, you got to think about, can we eat, part of a bar maybe, or actually, let's just say, that's actually more about B. In this one, we we're trying to find a linear function. You would want to think about, okay, as a constant rate of change, as I eat, each bar, it's going to constantly go up by 1. Am I going to constantly go up on the calories the same, a constant rate as well? And you would, because every bar you eat, you're adding another 130 calories every single bar you eat. So that is a linear function. It says B, as B increases by 1, because you can eat 1 bar, then 2 bars, and 3 bars, and so on. C increases by 130. So you eat 1 bar, it's 130. You eat 2 bars, that's another 130. You eat 3 bars, that's another 130, and so on. So the rate of change is constant for both x and y, even though we're using b and c to represent those letters. So it's a linear function. Letter B says, find the domain of the function. Is it discrete or continuous? So with this one, this is where we want to ask the question, can we eat part of a bar? And of course we can. We could take 1 bite of a bar, in fact, and we've consumed not 130 calories, less than that, in fact. So because we can do that, it is continuous then. So we could say it's continuous because we can eat, part of a bar. And so the domain then would just be b is greater than or equal to 0. So you could possibly eat 0 bars and get 0 calories, but you could eat anything more than 0, and that's continuous. Letter C says, now graph the function using its domain. And so when we want to graph this function, since we can eat as many bars as we want to, we're going to have to stop at some point. So we can start by doing an input-output table like we saw in the last one. This one doesn't say there's a maximum amount of bars we can eat, so we're just going to go with just eating 4. What about just those first 4? So if we eat 0 bars, we're going to consume 0 calories. So there's our ordered pair, 0, 0. If we eat 1 bar, we consume 130 calories. There's 130 for an ordered pair. Eat 2 bars, now this goes up by 130, it's 260. Eat 3 bars, goes up by another 130, now we're at 390. Eat 4 bars, now we're at 520. And so that is what we want to put on our graph, same type of graph that we saw before, just an L graph, since everything here is positive. We're not going to be able to eat a negative amount of bars, we're not going to be able to consume a negative amount of calories, so we can just plot these ordered pairs now here on this graph. And so we'd plot all those ordered pairs. Again, we're going to label it cereal bar calories. That's our title for the graph. We're going to label the x-axis as number of bars eaten, and we got 0 to 6 here. We don't need to put any more than that. And then on the y-axis, we're going to say calories consumed, 0 all the way up to about 800. And so then we can plot each of these ordered pairs, but since it's continuous, you want to connect the dots and show that it just would continue to climb as you would eat more and more bars. That's why the arrow is on the end, because that's what this domain would suggest, that it just keeps on going on into infinity in that positive direction. So you have to make sure you draw that line there. Once you've plotted the points, you connect the dots for continuous functions. Okay, so if you need to go back to that bit, just rewind this a little bit and get that copied down on page 67. At this point, though, I want you now to, on page 66, in the notes section there at the bottom of that page, just you're going to number 1 through 4. And so we're going to do a little lesson quiz here at the end just to see how much you remember. So 1 through 4, just number 1 through 4 for this page, and then we'll do another page in a second from 5 to 7 as well. So right here, number 1 through 4, go ahead and pause the video and do 1 through 4. Does the graph represent a linear or nonlinear function? Go ahead and pause the video and then check your answers. Alright, so here's where our answers are. Number 1 is definitely linear, it's a line. 2 is not a linear function, it's nonlinear because it's not a line. Number 3 It is linear because it does have this constant rate of change on both x and y. And 4 is nonlinear. It's got a constant rate on x, but y is not going down by a constant rate. So you're going from 8, this one's going down 4, this one's going down 2, that's not a constant rate there. Alright, let's go on to our next one. Now you get a number 5 to 7 on this next one. So again, number right there, the same place, just number 5 to 7 now, underneath where you did 1 through 4, or next to it. And now we're going to look at the equations. So this one, you're going to be asking the question, does the equation here represent a linear or nonlinear function? So go ahead and answer those, and then so pause the video, and then I'll show you the answers to 5 through 7. Alright, so hopefully you have answers now for 5 through 7. Number 5, that is a y equals mx plus b equation, so that is definitely linear. It's in that form of the y equals mx plus b. Number 6, this one can be tricky because you have this fraction, but look at where the x is. The x is up here on top in the numerator, and that's okay. That is linear because you can show it like this, where you can put the x next to the 3/5 fraction like that. So that means 3/5 is the coefficient multiplying x. So nothing's fancy happening to x, just being multiplied by a fraction. That's okay. Number 7 should be non-linear though, because you look at the x, it's being squared. So that's something fancy happening to x. So that's non-linear there. It's not in that y equals mx plus b format. Alright, let's look at a few more. Now you don't need to write these ones down, I just want you to see them. So number 8 would be another one about just a situation. So it's giving you the linear function here, m is equal to 50 minus 90, represents the amount of m dollars of money you have after buying D DVDs. A says find the domain of the function, is the discrete or continuous. So the question there about discrete or continuous is, can you buy part of a DVD? And of course you're not going to break a DVD in half to buy it. So that's going to be discrete then. It is discrete, and it's going to be, you know, like 0, 1 through 5. It's going to be a discrete function there. And then B says graph the function using its domain. So again, that's going to be the same idea as just an L graph like this. You can see we got the x-axis as the DVDs are purchased, and then the y-axis is labeled money left here. So right there's money. So you have and so on. So that's what we're doing on that one. Let's look at 9 and 10, and then you'll be done. Again, you don't need to write these down. Just watch them. I just want you to see them. So number 9, is this a discrete or continuous function? We got the number of stories of a building, and then the height of a building. So there's 1 story, it's 12 feet high, 2 stories, 24, 3 stories, 36. So we're going to be able to have a partial story of a building, most likely not. So this would definitely be a discrete function. Numbers of stories must be a whole number. You can't have a partial number, a fraction of a story on a building. Number 10, you got a 20-gallon bathtub is draining at a rate of 2.5 gallons per minute. The number G of gallons remaining is a function of the number of minutes, m of minutes. So does the situation represent a linear function? So again, you want to see, is it a constant rate of change as it keeps going down, 1 minute. So it's doing 2.5 gallons per minute. So after 1 minute, 2.5 gallons. After 2 minutes, another 2.5 gallons. So yeah, that's a linear function. It's going at a constant rate of change. So yes, it increases 1 minute and decreases by 2.5 gallons. That's a constant rate. So it's a linear function. And then the domain, find the domain of the function. So that would just be from 0 to 8 continuous. Okay, so that's why it's saying it's going to be 8 minutes after it's all gone, because after 8 minutes, if you do the math, you'd be down to 0 gallons. It would be all drained out. So it's going to take that 8 minutes to get to draining the tub. And this is the graph here where you got the minutes on the x-axis and the gallons remaining over here on the y-axis. It's going downhill, okay, because it's decreasing. The amount of water in the tub is decreasing, and notice it's all connected there from the 0, 2, 4, 6, 8. They just plotted those ones. You could have plotted all of them if you wanted to, but you just don't. They just plotted those to show the continuous function. Alright, so that's it for our lesson here on linear functions 3.2, and I'll see you again on our next one for 3.3.